Imagine a dry powder whose fine particle fraction is not affected by storage in high humidity. Wouldn't that be something? Hi, my name is Bishal Adhikari. I'm currently a PhD student at the School of Pharmacy, University of Otago. This presentation is on use of methionine and leucine to improve aerosolization of inhalable spray-dried amorphous particles. Among different excipients, amino acids being endogenous entities are commonly explored to improve aerosolization of inhalable high-dose spray-dried particles. However, apart from leucine, the use of other amino acids has not been well established. Recently, we have reported on successful aerosolization enhancement using methionine for kanamycin and antituberculin drug. The aim of this study was to access and contrast aerosolization enhancement offered by methionine and leucine, a known aerosolization enhancer using kanamycin as a model drug. Here, three different spray-dried formulations were prepared. The first with drug only, KO, and the other two with amino acids, kanamycin methionine, KM, and kanamycin leucine, KL. The amino acids were used in 1:1 molar ratio with kanamycin and a feed concentration of 0.2%. Weight by volume was used in all cases. Following production, a complete characterization was done using different techniques such as XRD, FTIR, low frequency Raman, TGA, DSC, SCM, and NGI. Further, physical and aerosolization stability of the formulations were assessed in three different relative humidity conditions, 15% and 53% at 25 degrees Celsius and 75% are at 40 degrees Celsius. Physical stability was extensively scrutinized using FTIR and Raman spectroscopy, and principal component analysis PCA was employed for data analysis as well as data visualization. The fine particle dose representing total particles with aerodynamic diameter less than or equal to 5 micron was calculated by interpolation of graph plotting cumulative mass deposited in different stages versus D50, and the fine particle fraction was expressed relative to emitted dose. Coming to results, the XRD with characteristic amorphous halos without peaks suggested that kanamycin only KO and kanamycin methionine KM formulations were amorphous, whereas kanamycin leucine formulation was partially crystalline with peaks at 7 and 18 degree 2 theta corresponding to a crystalline leucine. And the XRD and low frequency Raman suggests that the KM is amorphous. However, these techniques do not provide further information regarding phases in the matrix. Hence, modulated DSC was used to assess if the KM amorphous matrix was monophasic or biphasic. Coamorphous is the term used to refer to a single phase amorphous matrix. Such systems would show a single glass transition as shown in the diagram. The data suggests that KM is a coamorphous system as a single glass transition at around 90 degrees Celsius was observed. Now looking at the aerosolization, both leucine and methionine offered significantly improved fine particle fraction of the drug kanamycin. All the formulations had a similar particle size of around 1 micron. The particles of KO were spherical with pits resembling golf balls, as you can see in the diagram. The KL particles showed much more surface corrugation. However, the KM particles morphology only showed subtle difference to the kanamycin only formulation, suggesting particle aerosolization and deposition is a complex phenomenon affected by factors which are beyond particle size and morphology. In stability study, aerosolization could only be analyzed at 15% and 53% relative humidity, but not at 75% relative humidity at 40 degrees Celsius because of the conversion of the powder to solid lumps. All the formulations were stable at low relative humidity of 15%. However, at a higher relative humidity of 53%, aerosolization of kanamycin only and kanamycin leucine formulations decreased significantly, unlike that of kanamycin methionine formulation. Looking at physical stability, there was no change for KO and KL as shown in the diffractogram. However, methionine in the kanamycin methionine formulation crystallized out, as amorphous materials are known to be hygroscopic and kanamycin has a very good water solubility. Particle breathing was observed for kanamycin only KO in the SEM images. The TGA also showed an increase in water content, unlike for KO, particle breathing was not observed for KL or KM. KL did show slightly more water uptake than KM, but if that was the contributing factor remains unknown. The precise mechanism for such behavior is currently under investigation. The transformation behavior of the KM coamorphous system was assessed with extensive sampling using low frequency Raman and FTIR coupled with PCA. For spectral data, what PCA does is it reduces the dimensionality of data while retaining variation. It does this by identifying directions or principal components PC along which variation is maximum. Here PC1 corresponded to around 67% of explained variance and PC2 corresponded to 21% of the explained variance. Now, if you look at the loading plot in C, PC1 positive space corresponds to features of crystalline kanamycin, and negative space corresponds to crystalline methionine. In figure A, each spot represents a spectrum. The red dot represents spectra of samples stored at 15% relative humidity at various time points. Similarly, the blue one represents those stored at 53% relative humidity, and green one stored at 75% relative humidity. It shows that at 53% relative humidity, methionine crystallized out at fourth sampling point, which is 24 hours. Similarly, if you look at B, it suggests that kanamycin crystallized out only at 40 degrees Celsius and 75% relative humidity. Similarly, the PCA of FTIR also showed subtle changes in spectra, backing the data or backing the observation we had seen in the low frequency Raman. For example, in figure A at 40 degrees Celsius, 75% relative humidity, methionine crystallized out within 3 hours, as the positive PC1 space corresponds to features with crystalline methionine, as you can see in the loading plot in figure C. All in all, this study suggests that methionine offers a better aerosolization stability compared to leucine for kanamycin spray-dried particles. Plus, it highlights that physical instability does not always reflect on aerosolization. I would like to thank my supervisors, Dr. Samuel Das and Professor Keith Godin, for their support, and also Dr. Sarah and Carlis for help with the low frequency Raman experiments and data analysis. In addition, I would like to thank the University of Otago for doctoral scholarship and School of Pharmacy, Department of Chemistry for facilitating the different instruments used. Thank you for listening.